Okay, so we're down to the very, very last lesson, 6.3b. Class next week, both classes, Monday and Thursday, will be about going over the practice final exam. Now that we'll have covered everything. There will not be class on the Monday before Thanksgiving. So the 23rd of November. So a week from today, Thursday, November 19th, that will be our final class meeting. So around that time, I'll send out the password for the final exam, and then the final exam will be due during finals week. So you can take it anytime during then. And remember, your final will replace the lowest grade. So more important than ever to take the practice final exam and try to do well on it before you take the real thing, because there's more at stake here. I mean, the final counts for 25%, just like the other test, because it's not comprehensive, but you get extra credit for practice final, and final replaces your lowest grade. So if you have a low test score in there, this is your chance to really do something about it. Also, some time ago, I removed all late penalties. So if you have some old lessons in which you never got certified, you have the opportunity to boost the homework portion of your grade, because that's also 25%, by completing those lessons. Each lesson counts for roughly 1% of your overall grade. So if you're borderline, this could help you. So things to keep in mind. Okay, I'll get the screen share going. Okay, the previous lesson was about the indefinite integral. Today we'll see the definite integral, and the indefinite helps you evaluate the definite one. So I'll just explain both concepts here side by side. So the indefinite integral, we just have an integral sign and then some given function, f of x, and then followed by a dx. That is equal to some function capital F of x plus some arbitrary constant c, where big F is an antiderivative of little f. And to refresh your memories of what that means, the derivative of big F is little f. So you're carrying out differentiation in reverse. So little f is the derivative. You're trying to backtrack to the original function capital F. So for example, if little f is so if f of x is x, big F is x squared over 2 by power rule. And then for an indefinite integral, like in the previous lesson, don't forget to add on this plus c as an arbitrary constant. Okay. Now, the definite integral so that's also a given function, but now there's extra information. You're evaluating the definite integral on some given interval a, b. So both of these have to be specified. So it's an integral sign, but notice we have numbers a and b that are given. And you can see this from the first problem. We have an integral sign, there's a 5 and a 6. So a and b are the limits of the integral. And then you have your function, and then you have a dx. So what is this equal to? Well, you still need an antiderivative, but now what you do is you plug in the limits. So you have f of b and f of a, and then you subtract them. Okay. So a and b are referred to as the limits of the integral. So what do you do when so if you're given an indefinite integral, you're trying to find a function, big F, whose derivative is little f. If you're given a definite integral, so there's numbers here for the limits, you still get big F, but then you substitute in the limits and you subtract. So whereas the indefinite integral is a function of x, or whatever variable you have here, the definite integral is just a number. Okay. So this formula for the definite integral, where it's just the antiderivative at the limits and subtracted, that comes from what is called the fundamental theorem of calculus, which also says that if you have an integral and you take its derivative, you just they basically undo each other. That the derivative of an integral of a function is just the function itself. So really, the fundamental theorem of calculus says that differentiation and integration are basically inverse processes of one another. One of them, in a sense, undoes the other. Okay, so that's what lets us compute definite integrals without too much work. The definite integral has many possible interpretations, just as a derivative has interpretations. Derivative is the slope of a tangent line. It's the instantaneous rate of change of some quantity with respect to another. So the and there are many possible interpretations of the definite integral depending on the context. But the best known one is this interpretation of the definite integral is the area of a region bounded by two vertical lines, x equals a, x equals b, the x-axis, which is y equals 0, and the graph of f of x. So if you can imagine a region bounded on the left and right by x equals a, x equals b, on the bottom by y equals 0, and on the top by y equals f of x, this integral gives you the area of that region. That's not an application that we're particularly concerned with in this lesson. We're going to be using a different one where the definite integral can help us get the average value of a function between a and b. Excuse me. Okay, so now getting to the problems, evaluating various definite integrals. So for this one, we have the definite integral of 3 over x squared from 5 to 6. Now, you can think of this as 3 times x to the minus 2. And for that, you would use the power rule. So in fact, I'm going to write it that way. So 3x to the minus 2 dx. So now, in the factor of 3, you can just pull out of the integral. Constant factors you can always pull out. Okay, so I'm going to get rid of that. So then when you use a power rule, that'd be 3 times x to the minus 1. You add 1 to the exponents divided by the new exponents. Okay. And then don't forget the plus c. Okay. So now x to the minus 1, of course, that's the same as 1 over x. So 3 times minus 1 over x. So this is your antiderivative. So what we've done at this point is not the definite integral. This is the indefinite integral. Now what's left, so this is what we would have done in the previous lesson, but now the next step is to substitute the limits. The limits were 5 and 6. So whatever is the upper limit, you substitute that in first for x, minus the value of the antiderivative at the lower limit, which is 5. Now, when you are doing definite integrals, okay, we need this. You actually do not need the plus c. So from this point, you can ignore the plus c. Why? Because suppose I went ahead and included the plus c here and here. We're subtracting, they'll cancel each other out. So you just focus just on the function part of the antiderivative and plug in the limits. So minus 3 over 6. I'm going to put this on its own page. Okay. So now we plug in the limits 6 and 5 and just work out the fraction here, and we get 1/10. So that is the final answer. One thing that's worth pointing out here is that here you see this function is always positive because of the x squared. When you're carrying out the the definite integral of a function that's always positive, the integral should also be positive. So if you worked this out and got something negative, then you would know that you made a mistake. So questions about this first definite integral? Okay, because I got plenty more. All right. So here's our definite integral of minus 4 square root of x from 1 to 2. Now, square root of x is going to be positive, but then we have minus 4. So we should expect a negative final answer. Okay, so we're going to do the indefinite integral. So we go ahead and pull out the minus 4. And then square root of x is written as x to the 1/2 for purposes of applying the power rule. So we go ahead and add 1 to the exponent. That gives us x to the 3/2. And then the new exponent, remember, you divide by that. But that's the same as multiplying by the exponent flipped. So remember, I pointed out this pattern last time. We have these two numbers are reciprocals of one another. When you're using a power rule of a fractional exponent like this one. So then we get, after cleaning up all the constants, minus 8/3 x to the 3/2. So now we go ahead and plug in the limits. And again, you can ignore the plus c because it's going to cancel out anyway. So here we have our antiderivative of 2 plugged in, and then of 1 plugged in. And for 2 to the 3 halves, you would need your calculator for that. Okay. Reason why we get you don't have to do it this way, but okay, I'm gonna write it. This is because 8 is same as 2 cubed. So 3 plus 3 halves is the same as 6 halves plus 3 halves, which is 9 halves. But again, you don't have to do it that way. You can just do it like that. Okay. So when you work this out in your calculator, and this is what you get. Don't forget to round to 2 decimal places, so it'll be minus 4.88 in this case. Okay. All right, here's another definite integral of minus 2x minus 2. So we do the indefinite integral. We're going to use the power rule again. So here I break this up into 2 separate integrals. So integral of minus 2x and the integral of minus 2. Pull out the constant factors. So we're just integrating x and then 1. So from x, we get x squared over 2. And then from 1, we just get x. That's the constant rule here. And then this is our antiderivative. So now we ignore the plus c, and we go ahead and substitute the limits, which are 4 and 6. So upper limit is 6, so we plug that in first, minus the value at the lower limit. And this is our result. Okay, here we have 7 over x. We pull out the constant factor of 7. We have the integral of 1 over x, but for that, we get natural log of absolute value of x. Don't forget the absolute value. And then we'll plug in the limits. 8 is the upper limit, 5 is the lower limit. Okay, so we plug in 8 first, and then subtract the value we get from plugging in the lower limit of 5. Here, that's just one less thing to do in your calculator, but the difference of logs is the same as the log of a quotient. Again, not absolutely necessary. You can just work these out in your calculator individually, subtract, but it also happens to be equal to this. And there's some times where this property of logs is particularly helpful. All right, here our function is 2 plus 6 e to the x. So this is what we're going to need here, that e to the x is its own antiderivative. So I break this up into the sum of two integrals. So we 2 times the integral of 1 plus 6 times the integral of e to the x. So then these are worked out using a constant rule here and a rule for exponentials here. And then our limits are 5 and 6. So upper limit first, minus the value at the lower limit. And then you let your calculator do the rest. Okay, here we have an exponential again, but it's not e to the x, it's e to a constant times x. So it's important to pay attention to how to handle that. So when you have an exponential such as this, e to a constant times x, the antiderivative is itself, but you must remember to divide by the coefficient of x. So we need this 1 over k factor here. Now, 1.4 is the same as 7/5, although you can leave it as a decimal if you like. Again, that's just a personal preference thing. So we break this up into the sum of two integrals, integral of 1, and then integral of e to the minus 7/5 x. And when you take the integral, you have the integrand, e to the minus 7/5 x, but you divide by minus 7/5, so that's why we have this minus 5/7 here. And we'll just clean up the constants, and that is our antiderivative. So now, so now I go ahead and substitute in the limits. The limits that were given were 3 and 6. These numbers are actually random. It's kind of weird that 6 is always turning out to be the upper limit in these, which I believe is a coincidence. But so we plug in x equals 6 into our antiderivative, and then x equals 3. And then at this point, you need a calculator to work out all of these. So this is what we get with the exponents in decimal form. And then this is what your calculator would give you when rounded to 2 decimal places. All right, here we have application of a definite integral, I mentioned earlier, finding the average value of this function on this interval. So with that, we're going to evaluate the definite integral like before, starting with the indefinite integral. So we have 5 times the integral of x squared plus 7 times the integral of 1. So we have 5 times x cubed over 3, then 7x. I have to remember the plus c. So this is our antiderivative. And then you do a definite integral, like before. So we substitute in the limits, which were 3 is the upper limit and -1 is the lower limit. Watch your signs. Be very careful with your signs especially when you're plugging in the lower limits, since that value ends up getting subtracted. It happens very frequently that some kind of sign mistake is made during these steps. Now, to get the average value, so right here, 1 over b minus a times the integral of f of x, which should be a definite integral. Sorry about that. That's the average value. So this is a formula for it. So, so now we have 1 minus b, which is 3, minus a, which is -1, times the definite integral that was worked out earlier. That's a 224 over 3. So then when all of this is worked out, then that's the final result. So I'll fill that in here. Okay. So this is a thing to keep in mind. This is a formula for average value. So first you work out an indefinite integral, then plug in the limits to get the value of the definite integral, then divide by b minus a, as was carried out here. All right, here's another for average value. Okay. So this is a formula that was used last time. So now we take this function and carry out indefinite integration. Again, you don't have to convert it to a fraction. Again, that's just a personal preference thing. Okay. All right, so we have 3 times the integral of 1 plus 6 times the integral of e to the minus 0.4x. Actually, I'm going to write it as a decimal. Okay, so then what we have here is so integral of e to the minus 0.4x is itself divided by the coefficient of x. So that's where we have a minus 0.4 here. But then we wind up with, when we clean up the constants, we have 6 divided by minus 0.4. But if you work it out in your calculator, you're going to get minus 15. All right, so that is your indefinite integral. Okay. Now, the limits here are 1 and 4, so that's what we plug in. So here I plugged in x equal 4. Here I plugged in x equal 1. So then, once all that's worked out, I'll just express these as decimals. Sorry about this. Okay. So then once all that's worked out on your calculator, this is what you get. And then that has to be divided by the difference in the limits, so b minus a. So after all the arithmetic is carried out, then you round. You notice here more decimal places than needed are retained because you really don't want to round to the required number of decimal places until you get to the last step in case anything gets thrown off. Okay. All right. Last problem. So here we have a production level as a function of the number of units that are produced. So what is the average production during the first 7 hours? So that's the same thing as finding the average value of this function on the interval 0 to 7 because I'm okay. I apologize. I misspoke earlier. The production is the number of units as a function of hours. Okay, so X refers to hours in this case. Sorry, I was scrolling. My eyes were scrolling through this too quickly. Okay, so since it's during the first 7 hours, then we're talking hour number 0 as a lower limit up to hour number 7. We have a total time span of 7 hours. The difference between these two has to be 7 hours. So, and it's because it's the first 7 hours, that's why we go from 0 to 7. Okay, so we want the average value on this interval. No, Microsoft, I do not want to update anything at this time. Shut up. All right, so then breaking this up into two integrals, I have 210 times the integral of 1 minus 210 times the integral of this exponential. And when that's worked out, remember you divide by the coefficient of x. So we're dividing by minus 0.1, but that's the same as multiplying by minus 10. So when all the constants are worked out, this is what we have. All right, so we go ahead and plug in the limits, just completing the definite integral. And then we divide by the difference in the limits. And then again, wait until the end to round. And it turns out to be essentially 59. So the average number of units produced during the first 7 hours is 59 units. Okay. All right. We've actually come to the end. Are questions about any of these problems? I know you are like try to telepathically communicate with your classmates. Please, no one ask a question. Okay.
I actually do have a question. My mic wouldn't work. I don't know why my mic just broke. But anyway, on number 5, could you go back and just so that I could see what the answer was because I missed it.
Oh, sorry about that.
I know you're good. I looked down when you were saying it.
Number 5.
Let me write it down. Okay, thank you.
Okay. All right. Any other question? Okay, that's all the lessons. The focus is now on the practice test. That's what I'll be going over next week. So I'll stop recording at this point.